Hello, we're going to now look at developing an equation for finding the arc length of a curve. And after having done that, we're going to use that equation to actually solve a problem. And we'll look at the problem of trying to determine the length of cable that is required in the midspan portion of the famous Golden Gate Bridge located in San Francisco, California. All right, so let's begin with the first part. Let's try to develop this equation for the arc length. And a way I like to go about doing that is to take some curve. Let's suppose I have some curve here, whatever this curve may be, y equals some function of x, let's suppose. Right, and and I'm going to just put my y and x axes here. Okay, and what I can then do is take a differential, if you would, a triangle on this. Let me say I take a little differential width of dx and a height of dy, and then I look at this portion here, which I'm approximating to be the differential hypotenuse, which we'll call ds. The s here will stand for the arc length. And then what I could do is I can use the Pythagorean theorem. So therefore, by Pythagorean, I would be able to say that ds squared is equal to, of course, it's equal to the sum of the squares of the other two legs of this right triangle. So we can say dx squared plus dy squared. And now I would like to divide both sides by dx being squared. And if I do that, I get ds over dx, that entire term is squared, is equal to dx squared over dx squared is 1, plus dy over dx squared. And now I can take the square root of both sides. Okay, so these are some of my abbreviations. dbs stands for divide both sides, root on the s, bs stands for square root of both sides. And when I do that, I get ds over dx is equal to root 1 plus dy over dx, and that is being squared. Okay, now to try and wrap it up. So this is a very simple derivation, in fact. To wrap this up, I can multiply through by the dx, and I can also write this term right in here. You'll notice that from calculus you probably saw another way of expressing this as just y prime. Okay, that's this term inside of the parentheses. So if I do that, I can multiply both sides, if you will, by dx, and doing that I get ds is equal to root 1 plus y prime being squared. That's all in the radical, times the dx. Okay, so here is a nifty little expression whereby if I now were to integrate both sides of this, I can find s, where s, we're saying, is our arc length. Okay, so let's go ahead and apply that to the problem that I mentioned about the Golden Gate Bridge. And here is the problem statement. It says that we are to find the approximate length of the mid-spanning cable that's being supported between the towers of the Golden Gate Suspension Bridge. By taking the dimensions of the central span, we will say the central span is 4,200 feet. That means if I were to split this up, let's say this is my y-axis, my x-axis down here, and if the central span is 4,200 feet and I divide that into two portions, I could say that this portion right here is 2,100 feet, and of course this other one is also 2,100 feet, and the towers as rising to a height of 500 feet. Then we are then able to model the profile of this cable by a parabola where the x and y dimensions are in units of feet, and the parabola we can model is shown here. Now you may ask, how did we come up with that? Well, very simply, we just said y is equal to some constant times x squared, and all we did really is we stuck in the values. So for example, I came out to this point right over here, and I said this point over here has x and y values of 2,100 comma 500, and then I put that into this expression here. I said that c, we want to know what the constant c is, and it's equal to y over x squared, and now we just put in those values. So y happens to be 500 and x is 2,100, and we're squaring that. And if you do that, you'll find that with a little reduction, so you have to do a little reducing, you'll find that c comes out to what I have in that box. It reduces to 19 over 551,250. Okay, so at any rate, now we have an expression for y, and what I'm going to do then is, well, let's remind ourselves what the expression for the differential arc length was. So we developed the equation for the differential arc length to be ds is equal to root 1 plus y prime being squared times outside of the radical dx. Alright, so let's go ahead and therefore use this result. So the first thing I want to do is I want to find y prime. Okay, and so I'm going to say, well, y prime is equal to 19 over the 551,250, but I'm taking the derivative of this, so it's the exponent on the x, that 2 comes out, so comes down, I should say. So we have 19 times 2 on the top times x, and then we knock the 2 down by 1, so it's x to the first power. Okay, and so you could say that y prime is 38 over 551,250 times x, but really what we want is y prime squared, so let me go ahead and do that. So therefore y prime squared is going to be some rather large number. It will be 361 over, this is a very large number, it is 75 billion when you square the thing on the bottom, 75,140,625. So that's a huge number. Okay, times, of course, x squared when we squared it. Now, just so that I don't have to write this big number over and over again, I'm going to just call all of this here, I'm just going to call this k. Alright, so in fact, when I do the math, I'll just bring about the k, and then it's understood what k is, and we'll plug it in at the end. Okay, so therefore, we'll just say y prime being squared is equal to k. Now we know what k is, this stuff, times x squared. Now that we've done that, let's go ahead and plug it into this expression here. So I'm going to say, all right, so coming down over here, ds is equal to root 1 plus y prime squared, we just said is kx squared, dx. And what I really want to do is find s. Okay, so I'm going to therefore integrate both sides of this to find my s. So the integral of d of anything is that anything on the left. So on the left we just get the s when I integrate it. And on the right I get the integral of root 1 plus k x squared dx. Now we want to be a little bit careful for one reason. If I do my integration where x is going to vary between a couple of limits here, if I happen to choose, and this is the way I would prefer to do it, I would like to do my integration starting here at the origin and going out to this tower to the right. So I'm only going to find s to be this arc, okay? And once I find that, by symmetry, I'm going to double it and find the entire arc length. So to do that, that means I'm going to let x start at 0 and go out to 2100 feet. But in order to do that, then I'm going to multiply this by 2 and that by 2. So I'm going to double that to indicate that really this is really, in fact, s over 2. Okay? So the entire thing is what I'm really interested in, which we'll call s. All right. So, okay, now that we've done that, it's a matter of trying to evaluate this integral. Now, you may have asked yourself, why did I produce a series of videos on some of these trigonometric functions and stuff? We'll see that for this very reason, because we've already looked at things somewhat of this form, and a way to evaluate this integral is to do it by trig substitution. And so to do that, I'm going to say let's suppose that x is going to be, now this is 1 plus something, some term, and we have a square here. And so that reminds us of the trigonometric identity. For example, 1, so let me say over here on the side, so aside, we've seen this one a few times as well. Okay, let me even back up one step before that. Trig identity. Sine squared theta plus cos squared theta is equal to 1. Okay, so I'm doing this as an aside here. And if I divide both sides by cos squared, then I get sine squared over cos squared, that's tangent squared theta, plus 1 is equal to 1 over cos squared is secant squared theta. Okay, so I notice that what's sitting inside of this radical here is of the form of something like 1 plus something squared, in this case 1 plus tangent squared. So I would like my x to actually have that tangent in there, tangent of theta, but that k kind of ruins it for me. So what I will do therefore is I will divide by root k in anticipation that when I go to squaring x, I'm going to get 1 over k times tan squared theta. And when I sub this in for the x squared term, inside of the radical, the k's are going to wipe each other out from the top and bottom, and then I'll get 1 plus tangent squared theta, which is in fact secant squared theta. Okay, so let's do that then. So I'm going to say this is equal to 2 times the integral of 1 plus k times 1 over k times tangent squared theta. That's the square root. And one thing that we didn't do over here is we need to find out what dx is. So dx is, and this is one of those things that we said from an earlier video, you should memorize this. The derivative of tangent theta is secant squared theta, and we have that root k on the bottom, d theta. So I would say in the place of dx, we have here secant squared theta over root k times d theta. Okay, so let me separate these two out. Okay. All right. So therefore, we get here, this is equal to the root k on the bottom there is a constant. I'll pull it out. And by the way, I'll put a little placeholder here of theta just to remind us that the limits of integration changed between the former step and that one that we just did. And so this is the integral with respect to theta of root 1 plus the k's cancel, and then you get a tangent square. So 1 plus tangent squared theta, and then we have out here secant squared theta d theta. Okay, and then we know what that's going to be because we just showed it. So this is the integral. All of this stuff here is inside of the radical is secant squared theta. And so root secant squared, I get finally a secant theta times, of course, the secant squared, which was there, d theta, this portion. And so, see, now look at this. We get 2 over radical k integral with respect to theta of secant cubed theta d theta. And now, this is actually a really good thing for us because we've actually developed the integral of secant cubed theta d theta. I won't go through the derivation of that again here because we did that in a video that you can check out. It's actually the integral of secant raised to the third power. So if you need to see how that's done, please go and check that video out. But I'm just going to put the result in. Okay, so this is all then going to be 2 over radical k times the integral of secant cubed theta d theta comes to 1/2 secant theta tan theta plus 1/2 natural log of the absolute value of secant theta plus tangent theta. Okay, and we're not going to pick up a constant of integration because we have limits with regard to theta. Now, then, I really would like to convert back from my limits of theta back into my original variable, which was the x. Okay, so let's think about how to do that. So we said that, in fact, we said that if I were to look at this, okay, so let me draw a little schematic of a right triangle. We've done this before as well. So I have a right triangle here. Here's the theta. And we already know that we said that x is equal to tangent of theta over k. So we said okay, so recall that x was tangent of theta over radical k. That means that tangent of theta is x times radical k. Okay, and you may be saying, where did we get x is equal to tangent of theta over radical k? That's over back here when we were, this is when we were trying to make that trig substitution, okay, to integrate. Right, there it is. So now that we know what tangent of theta is, it's not a problem. I can say tangent of theta, this is equal to opposite over adjacent by definition. So the opposite then I'm going to set to be x times radical k. The adjacent will therefore be 1. And so this hypotenuse here is going to be, by the Pythagorean theorem, it's going to be radical 1 plus, so it'll be 1 squared plus this other leg of the triangle squared, that would be kx squared. Okay, so radical 1 plus kx squared is that other one. So now why did I do that? Therefore, secant, which you'll notice up in this equation that we have here, we have terms like secant of theta. We therefore would like to know what secant of theta is in terms of x. So secant of theta is going to be, think of it as the inverse of cosine. So if I can just find the cosine, I'll flip it and I'll have my secant. So cosine is adjacent over hypotenuse. That would be 1 over the radical 1 plus kx squared. So this is therefore going to be the inverse of that, which would just be the radical 1 plus kx squared. Okay? And so now let's go ahead and put all of that in. And so that means that, so let me say what I'm doing here. So converting back into original x variable, then I get that this is equal to 2 over radical k. And by the way, the 2's are gone, right? Because we had a half, and we had a half common to both of my terms, so that half and this 2 cancel. So I could really write this as 1 over radical k times secant theta, we just said, is radical 1 plus kx squared. Tangent of theta, we said, is x times radical k. Okay, so this is the tangent of theta, and this is the secant of theta, which is that term and this term respectively. And then we have plus, we don't have that half because it got cancelled with the 2 out there. We get plus natural log of the absolute value of radical 1 plus kx squared plus x times radical k. And now, of course, our x is going between 0 and 2100 feet. Alright, so I think it's pretty evident that the lower limit when x is 0 is going to make this term 0 because you have x times all this stuff. So 0 times all that is still going to be 0. And likewise, this term back here is going to drop out. And interestingly enough, this term here is just going to reduce to the 1, but then the natural log of 1 is 0. So let me just make a note here. Note, bottom limit where x is 0, it reduces expression reduces to 0. Let me just say reduces to 0 when you plug x equals 0. So all we really need to concern ourselves is with the top limit. So let's kind of wrap this up here. So therefore, the arc length S, which is what we were interested in knowing, is going to be 1 over radical k times root 1 plus k x squared, that's going to be 2100 squared, times x 2100 times radical k plus natural log of the absolute value of radical 1 plus k times 2100 squared plus 2100 times radical k. And I won't take the time to do this with a calculator. You can get your calculator out and put it all in, where once again k, let's not forget what k was. K was this value right here. Okay, so it's that 361 over 75,969,140,625. So let me just write it down here so you'll remember it, where k is equal to 361 over 75,969,140,625. Okay, and when you plug all this in, you should be able to show and find that therefore S comes to, at least when I did my calcs, it came to about 4,000. So let me put an approximation here. Approximately 4,215 feet. Okay, of cable at the midspan of the Golden State Bridge. So that's quite a long strand of cable, because when you think about how many feet there are in a mile, let me just make a little note here. Note, there are 5,280 feet in a mile, right? So it's not, that's a lot of cable. When you consider that we're just off by about 1,000 feet or so from being a mile long, just in that one leg of that center spanning cable. Okay, I hope that was something of benefit to you. I hope it was also understandable. Go ahead and send me questions if you have any, and support the website if you are liking these educational videos. By all means, then we would like to see you like us or subscribe to us, and we will see you in a future video. Thank you very much.